Oh, Grant, let me talk to you after class. Okay, so here, of course, n is in the natural numbers. So z omega, in the case that n is 1, is exactly the quadratic rings of integers we've been talking about. If n is 2 or bigger, these are subrings of z omega that have the same quotient field, but they can never be UFTs because they're not integrally closed, right? Only the full ring of integers is integrally closed, right? So it's a very natural question to say, hey, you know, what's the best you can do? You can't have unique factorization. Well, let me point out. As it turns out, so here, this ring right here is this ring with n equals 2 and omega is 1 plus radical negative 3 equal to 2. This one is an HA, right? Which again, arguably is the best you can do since you can't possibly have any difference. It's not even close. So just as a curiosity, I might ask, how do you think that you might go about trying to prove this? Well, I'm going to produce a tool that is sometimes useful and applies in this case. Theorem. What are with E and U? Well, every irreducible of R is irreducible in T, then R is at least. So if you've got a situation where you've got little one inside big one, and you know two things, you know little one is atomic, right? And you know that every irreducible and little one is still irreducible upstairs, then yeah, it's easy to take, then R has to be accepted.
Doesn't it suffice to show that to have the T as an HF?
Yes, absolutely. Yeah. I was just thinking about this example here. Actually, you're right. And in fact, let's do that. Right, this is even more loosey-goosey. Um. The irreducible factorizations. So of course, what I mean is each pi I and each little tornado guy, they're all irreducible, not only in R but in T. This is a factorization. T as well. And an irreducible factorization. Because all the irreducibles downstairs remain irreducible upstairs. Hence, K equals L as T is an HFT. And there you go. You may wonder where I use the hypothesis that R is atomic. Without that hypothesis, what you get is R has the following property. Any two elements that can be factored into irreducibles do so, or any element, any two irreducibles factorization is the same length, the same element, must be the same, but it may not be atomic. So an atomic domain also has to be an HFD, or I'm sorry, an HFD also has to be atomic. So since all irreducible factorizations of same element are of equal length, and are atomic, then R is by the way, you might ask yourself, is it possible that T be a UFD and a subring not atomic? I'm gonna be a smart aleck with this. Yeah.
Because we have an example of a domain that has no atoms from the beginning of class, but just take its fraction field.
Right. Yeah, that's my smart aleck answer is, right, take anything that's not atomic and look at its quotient field. Right, and there's kind of a trend of examples. And usually when examples are that easy, that means that they're all over the place and there's all kinds of dirt going on. Okay, so we're going to use this theorem that if you have an atomic domain inside a domain that's at least an HFD, and every irreducible remains irreducible here, then you preserve the HFD branch. So I'm going to make a claim. So this is the big overriding. And remind you, C square root -3. So somebody brought this up last time correctly. I think that, sometimes they use the plus and sometimes they use the minus here. I'm using the minus here on purpose because this is a primitive cube root of unity, and I've already kind of got the computation set up for that. But it doesn't matter. You can restructure this plus. So I make the claim if by the way, let me point out that this ring here is a unit. And in fact, we showed this last time, using the Minkowski value. In fact, the Minkowski value was less than one, or I'm sorry, it was less than two. Right. So suppose you have an element here. Then and so here's what this really says. I'm gonna add a little bit more to it. If you have any element up here, you can hit it by power of this cube root of unity and knock it down into the smaller ring. What is more, if you have two distinct elements in this range, such that omega n1t and omega n2t are in R, then omega nt is in R for all. So if any two different powers, both knock t down in there, then every power works. And basically, this is just kind of a mock two argument. So I've got a lot of claims here. State my claim here. Proof of claim. Right T X plus Y omega, where X and Y are in this. Right, this is what a garden variety element for this ring looks like. It's an integer plus an integer times omega, where omega is a cube root of unity. Now, well, let me ask you this. Does anybody, well, let me go this here. So T equals X plus Y omega. Omega T is Y squared omega plus X omega. Y, whoops, break out there. And let me point out that omega squared plus omega plus 1 is 0. That's sort of a minimal polynomial relation for the cube root of unity. And so in particular, omega squared equals minus 1 minus omega. I'm going to use this rather liberally. So this actually becomes minus y plus x minus y omega, I believe. And finally, omega squared t is x omega squared plus y. Because of course y cubed is 1. And this is equal to y plus or I'm sorry, y minus x omega. Now, can anybody give like some kind of oomph to my claim here? I think it's real close.
ring. If and only if the coefficient of omega is even.
That's right, that's the key observation, right? What does it take to blast this down into this ring? Basically, what you need is an even coefficient for your omega, right? So let's kind of deconstruct this. Number one, if y is even, t is already an r. So omega to the 0 works. Correct? Two, let's see. Let's take the last case first. If x is even, omega squared t is an now, what about that middle case? What does it take here? Well, so we've got this licked if y is at even. We've got it licked if x is even. What's the only thing we've got to worry about? And that is if both y and x are odd. Omega t. And in fact, I get my what is more out of this, right? Because notice. We want to establish this here, right? Well, let's also make the following observation. I want to establish this here. What is more, if you have two distinct ones, then it always works, right? So suppose, what do we got? 0, 1, 2. What happens if 0 works? Well, what if 0 and 1 works? Well, for 0 to work, it is necessary for y to be even. And for 1 to work, then actually this isn't well, this thing has to be even. So if that means that x has to be even. So for 0 to work, y is even. And then so is x. Because right here, in this case right here, you need x minus y to be an even number. You already know y is even, so x is even, right? For 0, 2 to work, this means y is even. And for this to work, x has to be even. Agreed. And the final case is for 1 and 2 to work. Well, this means for 2 to work, or I'm sorry, for 2 to work, then x is even. And for 1 to work, then x and y both have to have the same parity. And therefore they all work, right? Because if both x and y are even, then every one of these outcomes here, this is in here, this is in here, since they're both even, and this is in here. And so that gives you the what is more statement. So if any two different powers work, they all work. And you see what the key is. For this thing to work, it has to be in the ideal generated by 2 up here. Right? Okay. Any questions so far? Okay, so, so now I'm going to claim that, and this will kind of finish off this. Unique numbers. You're reducing. And this is gonna kind of be a big crux thing. Alright. Suppose R is in R. And R equals alpha beta. Alpha beta. I'm going to show you that R reducing upstairs meant that R has. We know from claim 2 that there exists, let's say, M in the interval from 0 to 2, such that omega M alpha and omega N beta are both in R. Right. So let's multiply these two together. And what we get is correct. Now, if M plus N is equivalent to 0 mod 3, we have so in other words, if this is a multiple of 3, then this is just 1. And so we've actually, there's your reduction, right? Because both of these factors are in R and it reduces. What if not?
Power of omega.
So omega to the K R is in R. And so how does that help?
One to the R times omega 2 to the R is equal to
Right. So can you run that by me again?
I was gonna say, like, you could multiply 2 different powers of omega to the R, but R back using that omega, so
Okay. So let's take this one step further. So this means. We're on one of these. I'll take this a little bit further here. So, like X equals, say, X. Now notice the product of these. Yeah, and of course, these are the elements up in T here, and it's alpha beta. We change this notation, so it's just. Okay. Notice that alpha beta equals alpha 1, beta 1. Well, I'll go ahead and bite the bullet. Plus alpha 1, beta 2, plus alpha 2, beta 1, omega, plus alpha 2, beta 2, omega squared. All right, let me rearrange this a little bit. Minus alpha 2, beta 2. Alpha 1, beta 2, plus alpha 2, beta 1, minus alpha 2, beta 2. And this is my famous R. Everybody okay with it? Now, what we've learned in this case is R absorbs every power of omega. So what does this say about these coefficients here? Right. Since R omega T is in R for all T, alpha 1 beta 1 minus alpha 2 beta 2 is equivalent to 0 in rod 2. And alpha 1 beta 2 plus alpha 2 beta 1 minus alpha 2 beta 2. No, that's right. Okay, so what can we conclude from this, by the way?
Divides,
Either both alphas or both betas or even.
That's what we're going for. So let's suppose. Beta 2 is odd. Let's see. Well, yeah, I just took this cases. So this means. So what this, Grant, right, what this should mean is, one of these is odd. So my claim is if beta, one of these is odd, then if beta 2 is odd, I claim that both alpha one and alpha two are even. Let's see what happens here. If alpha two is odd, then what does that mean? Well, if alpha two is also odd, then that means that both alpha one and beta one are odd. Right, agree. So in this situation, what we have, beta two is even, and it's the only one. Right? Oh, I'm sorry. Alpha. Beta one is odd, and if alpha two is odd, okay, everybody's odd, right? And that contradicts this equation. Right? Odd can't be even. Right. All right. Subcase two, if alpha two is even, and alpha one is odd. Let's assume this. So we have, what do we have? We have beta two and alpha one are odd and alpha two is even. What is the status of beta one? Well, let's see what we've got here. Alpha two is even. And so what does that mean about beta one? It has to be even as well, right? Alpha two is even. If alpha one is odd, then beta one is even. So we have beta one is even. We have alpha one is odd and beta two is odd. So that's equivalent to one. That's equivalent to zero. That's equivalent to zero. And that's a contradiction. So this is also a contradiction. And so it looks like it might not be. Let's see, can we go through the same thing? Yeah, and this is symmetric, right? So the same argument. So one of alpha beta has all even coefficients. Without loss of generality, alpha equals alpha one plus alpha two omega, with alpha one, alpha two even. Right, okay with it? Therefore, omega T alpha is in R. So this property has to be inherited down. So to one of the factors. So if R is alpha beta, if R absorbs every power, one of its factors has to. And now we totally got it. Because what do we have? So I can use any power there. So I have omega n beta times omega minus n alpha is equal to R. And there's your factorization in R. Everybody okay? Who would have thought a bull mod 2 argument would take so long? There we are. So every irreducible in is irreducible in C, which is UFT. Of course, all we need is HFT, just pointed out before. So By the way, z adjoint square root of -3 is certainly atomic. Can somebody tell me why? It's a blast from the past. Now, what would any say? There you go. It's a theory because it's a homomorphic image of CX. All right. Okay. So, any questions? Let me give you a proposition. So this opens the door to HFDs inside here. So here's what we have. What about other stuff? Right? What about any of these HFDs? Right? I mean, perhaps they can be all over the place, but perhaps surprisingly, they're not. There. And that's 11 through 6. Omega equals square root of D in D equal to 3 minus 4 and 1 plus radical D equal to 2 if D is equal to 1 minus 4 and here D is less than 0, hence the imaginary. I'll re-emphasize this then for n bigger than 1. By the way, we know what all the UFDs and HFDs are when n equals 1, not because of me in particular, but because of, you know, this business I gave the list, it's been discovered. And for n equals 1, Z n omega is an HFD. If and only if D equals -3. So in other words, we've already found the only one. Because when n equals when D equals -3, that's inside the quadratic field Q adjoint with the square root of -3. So it's n equals 2 is this one. So this is what we just did, because this one right here is Z adjoint square root of -3. And what we showed essentially is, actually, what we should have picked up from that proof is really, this is almost a UFD, it's just missing some units. So here's sort of the action that happens here. Here's my favorite factorization in Z square root of -3. right? Two different factorizations. And these elements are all, I mean, this is perfect square, these sort of look different, right? But in fact, and actually, I guess I should have done, let's do this just to make my life easier. Because this is the omega thing, but it doesn't matter, you can do it the other way. In Z omega, these two are essentially the same thing, right? Because ooh, I'm so clever, right? But this is just really, this is omega. So in this ring here, these two are essentially the same in the sense that they're associates. They vary by a unit, even though they're quite different down here because you don't have this intermediary. So the only reason that your factorizations fail is you don't have the units to put it together, right? So what happens here? Maybe I can get them half the other direction. This, of course, this is the interesting part, that any HFD, that this is the only one, right? Let's suppose first that D is equivalent to 2 or 3 motion. And of course, if this theorem is right, I should find nothing here. There shouldn't be HFDs, right? So let's see why that's true. We show that in this case, of course, your omega is radical D. You have different length factorizations. Any ideas on how we might go about that? Well, I'm gonna make a claim first. I claim that in Z adjoining N radical D, that N radical D itself is irreducible. In fact, this is imaginary, it's quite useful. The norm is much more friendly in this case. Let's first, let me first point out that if you take the norm of A plus B in radical D, this is A squared minus D n squared B squared. So suppose A plus B in radical D divides in radical B. Oops. Let's just suppose that forgives. Well, this means the norm of A plus B in radical D divides the norm. Then radical. So in other words, a squared plus, or I'm sorry, minus d n squared b squared divides minus d n squared. So what can we conclude from this? Right, that is correct. B must be 0, right? And the reason is, remember, D is negative. So this sucker, these are both positive, these are both positive integers, right? And notice that if B is 1, or if the absolute value of B is 1 or greater, then this thing is bigger than this. No way is it going to divide it, right? So this is kind of a size sort of thing, because B equals 0 or a squared minus d n squared b squared is actually bigger than minus d n squared. Correct? So B must be 0, but so a plus b in radical d equals a, and no integer divides in radical d. Because if an integer a divided that, that would mean that it's a smaller n that multiplies radical d to be in this order, right? And radical d is sort of basement, right? No integer can divide that. So n radical d must be irreducible. Now, check this out. So if you look at n radical d times minus n radical d, you get minus d n squared. Here you have two factors. And here, well, first of all, n is bigger than 1. So this has can only have two factors. Well, what are we forced into here? D must be -1 and n is prime. That's the only possibility. So right now we've thrown out everything. So now what can we conclude at this juncture? We can conclude that the only HFDs are of form Z adjoint PI. P is a prime. They have to be prime index in the Gaussian universe. Now, I'll leave you this for Thanksgiving. Just check this for me. It's easy to check that this and its conjugate are actually both irreducible elements of ZPI. And when you multiply this out, you get 2 times P times P, and there's your contradiction. These are irreducible, 2, and there's 3 over here. So already we know that there are no HFDs that live inside of that are of this form. The only thing left is D is equivalent to 1/4. In which case we need to have 1. We can't just eliminate it. Okay, any questions?
What is known for the real quadratic case?
Nothing. Right. I think that actually it's recently been shown that I think you can have infinitely many HFDs inside one fixed UFD, but I'll have to check on that for you. But it's not even known if there's infinitely many real quadratic UFDs in the interval closed case. So anyway, I hope you all have a happy Thanksgiving. I've got to kind of skedaddle because I've got to torture my Go to, when you're out. Students.